Active filters use active components like an op-amp or transistors. And there are a variety of reasons why you might end up doing this. If you're trying to build a passive filter, and particularly a higher order passive filter, you're going to have to use inductors. And inductors can be very expensive, they can be hard to implement on an integrated circuit, and so often using an op-amp is the better way to go there. So op-amps can be advantageous over inductors. Another advantage would be impedance control. So by using an op-amp in my filter, I can provide a higher input impedance than I might have out of an RLC filter. And then finally, a third advantage is that I can provide a gain in addition to the basic filtering part of my circuit. So let's look at a particular active filter topology and then go through and analyze that and see what kind of filtering it actually provides me. In addition to the op-amp, which defines this as an active filter, I have a capacitor that I'm calling C. I have two resistors, R1 and R2, and obviously an input voltage and output voltage. My non-inverting input is connected to ground, and I do have a feedback path from my output to my inverting input, putting this in negative feedback. I should also mention that a disadvantage to using an active filter, of course, is that I need a power supply now for this op-amp. And so if you want to get away with as few components as possible and not have a power supply attached to your circuit, you might want to go with a passive filter. But active filters do have a lot of advantages to them. So let's start by analyzing this circuit. And I'm going to start by creating a equivalent impedance to this R1 and this C term right here. And those impedances are in series, so they're going to add. So I'm going to set my equivalent impedance equal to R1 plus 1 over j omega C. And that would be equivalent to 1 plus j omega R1C over j omega C. So now that I have that, this is a basic inverting amplifier topology. So I know that my V out over my V in is going to be minus R2 over that equivalent impedance that I have. That would be kind of my R1 in a very basic inverting amplifier. So I can write that out by substituting in this term for my equivalent impedance. And I'm going to get minus j omega R2C, right, this denominator here multiplied by negative R2, over 1 plus j omega R1C. And I'm going to pull out some of the resistance terms here. So I'll rewrite this once again as minus R1 over R2. So there's the gain term that I get from this active filter times 1 over 1 plus 1 over j omega R1C. If I'm interested in looking at this performance as a filter, I want to look at the magnitude ratio of this term here. So I'm going to take the magnitude of V out over V in. So VO over VI and the absolute value of that. So I have a complex term here. This is going to equal R2 over R1, once again my gain, and it is an inverting gain here, times the magnitude of 1, just 1 here. And then in my denominator, I'm going to have 1 plus the magnitude of this term right here in the denominator. I'm going to have my real part squared plus my imaginary part squared. So my imaginary part, if I multiply both these sides by j, so I'll have 1 plus 1 over omega R1C, that whole thing squared, and that under the square root. So this is my magnitude ratio, so I can think of this as my m of omega for this filter. And one of the things that I can see in this is I have this R1 over C term, so my omega C, my corner frequency here, is 1 over R1C. So using that, I can rewrite this again, and I'm going to get my magnitude as a function of frequency will be that R2 over R1 times 1 over the square root of 1 plus, in this case, omega C over omega squared. Right, so this looks fairly similar to what we talked about previously for a first order filter. In this case, the omega C over omega is flipped, so let's see what kind of impact that will have on the functionality of the circuit. So if I look at this and I look at an omega is much less than omega C, right, then this term is going to be dominant, right? Omega C is large in comparison to omega, so I'm going to get this R2 over R1 term times 1 over omega C over omega. So I'll get omega over omega C. So in this case, my magnitude ratio here will be that gain term, R2 over R1, times omega over omega C. If I have the case where omega C is much smaller than my frequency that I'm operating at, in that case, my magnitude ratio, this term is going to be very tiny, so I'm just going to get that gain, R2 over R1. This thing will be 1 here. Right? So what this is telling me is that when omega is small, this gain is attenuated, right? I have a smaller fraction of my input going through to my output. If I'm at higher frequencies, so I'm much above that corner frequency, then I'll get my normal gain. So imagine R2 is equal to R1, I'll just get a magnitude ratio of 1 here. So what this is telling me is that this is a high pass filter. Right? My higher frequencies are getting through, in this case with a gain as well, because I have this active filter, and my lower frequencies are being attenuated. This also tells me that this is a first order filter as well, because I have that K equals 1 term down here. So that is my K equals 1, which indicates a first order filter. So this op-amp circuit right here with these reactive components like a capacitor are giving me both a gain, this R2 over R1 term, and the filtering that I might want. So this is a very common topology for a first order high pass active filter. I'm not limited to first order filters for my active filters. I can also have higher order filters using op-amps as well. This will be one very common topology that you might see. This particular filter is called a Sallen-Key topology, and this is very, very common. And the key part of this happens to be a low-pass filter design, but I can take these positions that I have these various impedances. In this case, I have my resistors here, and I have my capacitors here, but I can move around these capacitors and resistors as long as I keep 2 capacitors and 2 resistors and get a lot of different behavior out of this circuit. So I could get a high-pass filter, I can get a band-pass filter. There are a lot of different filters I can ultimately get. This happens to be a second-order low-pass filter with, in this case, a corner frequency that will be 1 over the square root of R1, C1, R2, C2, right? I get units of second squared down here, which is why I have the square root there. Another possible thing that I can do with these is I can cascade them, right? I can set up one after another, and I can effectively think of that as multiplying transfer functions together. So I can cascade to get even higher order filters out of this topology. Right, so I would have one Sallen-Key topology followed by another one to get much higher order filters and that much steeper transition between a pass band and a stop band. So this is a low pass second order filter. You can do the analysis of an op-amp circuit, right? You call this a particular voltage, calculate the voltage at V+. You know that V- in this case is V out. And then just do your KCL on that feedback on this path right here. And you could calculate VO over VI, calculate the magnitude of that, look at M of omega, and see, in fact, using that this is a low-pass filter. This also happens to have unity gain, so it does not have any gain at 0 frequency.